Thank you very much for some kind presentation. And also I would like to thank to the organizer for inviting me to give this lecture in this important meeting. So, well, as Professor had already said, I come from the University of São Paulo in Brazil. And I would like to present you tonight, or well, for me tonight, for you this morning, this some result by using ionic liquid as electrolyte in and this behavior in one material for a negative electrode and another material for a positive electrode to show that perhaps in the future ionic liquid could be a nice electrolyte to use in some kind of device, a special device like batteries. So before I would like to show you what is an ionic liquid, and the best one is to compare a little bit the properties of ionic liquid with a commercial electrolyte that is normally used in batteries, like the mixture of ethylene carbonate, dimethyl carbonate, add a salt like hexafluor phosphate, lithium hexafluorophosphate, of course, for lithium batteries. So this is the regular commercial electrolyte, and that is an organic mixture of organic solvent with the lithium salt. If we compare with ionic liquids, that normally you have there are salt that they are liquid at room temperature, and normally between 10 degrees centigrade until 100 degrees centigrade are considered ionic liquids. Of course, that you can have an ionic liquid with sodium chloride, but this is at 800 degrees centigrade. So the important thing of ionic liquid that you have a big families of different cations, like imidazolium, piperidinium, pyrrolidinium, and you can also change the substitute in this cation, so the family is really big. And also you have a very nice families of different anions, like bis-trifluoromethyl sulfonylimide. This is an anion that is widely used for electrochemistry because it's very, very chemically and electrochemically stable. The bis-fluorosulfonamide also is very nice to do electrochemistry, and of course to use them, for example, as electrolyte in batteries. So the combination of this cation with different ions give you a liquid with different physicochemical properties. Like, and for us, for batteries, the more important thing is the transport properties, means the viscosity and conductivity. So in this liquid, you have only cation and anion. There are no neutral molecule of solvent, and of course that give you liquid that with a high viscosity. This is not good for us for electrolyte. However, we can work on it, trying to decrease viscosity and to have another important properties. So if you have how this property are fixed in the case of ionic liquid. So here we have the normal solution of organic solvent with, for example, a lithium salt. In this case, it's a tetrafluoroborate lithium. And of course, you have the solvation of the cation with the solvent molecule. And all this solvation depend of the concentration of the salt in this solution. In the case of ionic liquid, it's a little bit different. This is a snapshot of dynamic molecular dynamics. So you have here the lithium cation. If we put the lithium salt in the ionic liquid, and here you have the coordination of this cation, of the lithium cation, with the anion. This in red are oxygen on the TFCI anion. So in this case, the coordination there are not a solvation of solvent molecule, but a coordination of the anion of this ionic liquid. So this means that the solubility of the salt in this ionic liquid depends of the capacity of the anion of the ionic liquid make the coordination of the lithium salt. Okay, and this the way that the anion coordinates the lithium in this case also depend of the lithium concentration. So the main drawbacks for to use these ionic liquids as electrolyte is the high viscosity. There are the lower the viscosity of an ionic liquid is more or less 50 millipascal per second. And of course, there are another important property that is dependent on the ionic liquid is the solubility of the lithium salt that you need to dissolve in the ionic liquid. So if there are this kind of drawback, because why there are many people working trying to find out how you can use this ionic liquid as electrolyte. So one of the very nice properties of the ionic liquid is that there are the wide thermal stability. So here we have 3 ionic liquid, almost always with the same anion and changing the cation. Here we have a kind of imidazolium that here in this position you have a hydrogen. Is a imidazolium with the position of the methyl here, and here you have the same imidazolium that here, but with the different area. So to see what happened with the thermal stability, we put this in a typical battery coin cell, and with we run the accelerating rate calorimetry, and we compare with the change in temperature by decomposition inside the battery regarding the temperature outside the battery. And here you have the change in the temperature when begin the decomposition of the organic commercial organic electrolyte, and here you see what happened when you have the ionic liquid. So you can see that the stability of the ionic liquid is really better than the organic solvent. So you have an impact of all the security of the battery if you use ionic liquid. So this is a very nice characteristic of the ionic liquid to use that. And the other thing is that you have here different ionic liquid and the electrochemical window. So you have a good thermal stability and an excellent electrochemical stability, and this is the main properties that are really nice to try to build and synthesize ionic liquid that can use in a good way with in batteries. Okay, so as a positive and negative material, I choose to show you in this talk the case of silicon that is widely studied, and they have some advantage in the case of silicon regarding to the charge capacity if we compare with typically acid negative electrode with graphite. So the problem of silicon is that there are many drawbacks, and these drawbacks are mainly related with the change in volume. With you have the charge discharge reaction, and also the problem of the say the formation of the solid electrochemical interface. So the idea to use here ionic liquid is to see what happened with all these drawback regarding silicon, and if you have a better electrode material in these cases. This is only to put you the reactions during discharge and charge in the case of silicon. Okay, so regarding the positive material, I have chosen an spinel material, the manganese spinel, because in this case the limit potential, or the potential during the charge discharge, is greater than the case of lithium, the cobaltated, the lithiated cobalt oxide, or the case of the LIBs. So and this is also another nice characteristic, and this, you have 3D diffusion channel that can allow to grow to have a better diffusion of the lithium anion inside the structure of the spinel, the manganese spinel. The drawback is that you suffer with the Jahn-Teller distortion, and this lead to a poor cyclone stability. So also we will see what happens when we use ionic liquid to do the charge discharge of this kind of material. Okay. So in the case of silicon, we use the butyl methyl pyrrolidinium with FSI as an ion, and with 2 different salt concentration. And in the case, and another ionic liquid that you have used is the butyl methyl pyrrolidinium with TFSI. So these 2 ionic liquids have different viscosity, and as you can see here, in the case of the FSI, the viscosity is smaller than in the case of TFSI. And the other important characteristic of the ionic liquid is when you change the concentration of salt, you have an increase of viscosity, because you change the structure of this ionic liquid. It's like a compaction of the ionic liquid. This is completely different than you have normally organic electrolytes, that when you change the concentration, you have not many changes in viscosity. Another thing that is important is that the conductivity is better for the case of FSI ionic liquid than the FSI. And another important characteristic that is not good as electrolyte is when you add the salt, so you have an increase theoretically in the number of species that can transport charge. You have even that a decrease of the conductivity due to the increase of viscosity. So you can put all these in the case of in a Walden plot, And this is a theoretical line for a normal electrolyte, and what happened when you put all the things for both ionic liquid, and of course, always it's a little bit better the case of FSI than TFSI. All this is very important, but because they can impact the battery if you want to take out bigger currents, because in this case, all the transport phenomena will be really important. So, okay, so here we have the silicon electrode with, and this is the commercial, the charge-discharge curve with the commercial electrolyte, typically for silicon. And you can see here are two different ionic liquid. One is a phosphine ionic liquid, but I want that you see this one, that is the butyl methyl, the FSI anion, and you see that you have a better behavior of the in this case the lithiation capacity, and we try to understand why it's better in this case than the case of the commercial electrolyte. So one of the things that we need to see is what has happened with the chemistry at the interface, because you have a big amount of anion and cation, and this interface, and you have no neutral molecule solvent, so the chemistry could be really different. So this is a voltammogram at 1 millivolt per second in the two different ionic liquid, and you see that the FSI, you have a better curve. The charge involved here is bigger than the charge that you have in the TFSI. Okay, so it seems that to use this ionic liquid is better, that the FSI anion is better than the TFSI anion. Okay, so when we make the charge discharge curve, and here we put the lithiation specific capacity, you can see this really good. You have when you increase the current that you apply, you see per gram, of course, and you have that the capacity of when you use the ionic liquid with FSI is really better than the case when you use the FSI, that it decayed almost at zero, very fast with the number of cycles, and means that the silicon suffer a very dramatic change when you use the FSI instead FSI. So it seemed that this is better, and well, they did another kind of experiment to try to identify what is happening with the SAI layer, and we think that in the case of FSI, you have a very compact layer, and after I will show you some XPS experiment, not in the case of the silicon, but in the case of the spinel electrode, to show that you have the formation of this protective layer in both cases. So it seems that when you have the ionic liquid, you have a better protection, and this layer also have some kind of influence on this change of volume in the case of the silicon electrode. So going now to the spinel electrode, we use this spinel, we dope it with titanium. The idea to dope is very well known, is to avoid or to have a diminution of the Jahn-Teller distortion, and you can do you can have a better charge curve with time. In our case, we make a composite with a graphene material that is made by the thermal decomposition of organic molecule, and the idea to put graphene there is to improve the electronic conductivity between particles. So we did all these characterization that you have some kind of graphene there. Of course, that we have also all the Raman and XPS characterization also. So with this material also we change a little bit the surface area of the material. That is good, because it is possible to have more a better malleability of the ionic liquid with the material. And here is the curve for the organic commercial electrolyte. Is only to show how it's better to use this graphene with the spinel electrode, and the differentiated of charge by potential show that they have different position in both cases for the intercalation of lithium. Okay, so now going to ionic liquid. Here we use the lithium TFCI salt with the pyrrolidinium cation, and here you have the curve. In black is the commercial one, in the green is the ionic liquid. They are similar. That is good, because the ionic liquid is more viscous, so this can put some problems. And of course, that this is for in this case we show for different current using for the discharge and charge process. And for example, in this case, at 25 degrees centigrade is not very good for high current for the charge discharge process. So to see what happened if we change temperature to have the diminution of viscosity and to improve all the transport properties. So you have, for example, for high currents, here is at 25 degrees centigrade for the ionic liquid, and for the same ionic liquid at 40 degrees, you have a better charge discharge property. So the influence of temperature is for higher current. That is interesting, because it's a way to improve the behavior for a high rate of charge discharge. Okay, so also we have the two different lithium that are in the structure. So, and here you have all these for this three temperature, and the shape are very similar. It seems that there are a difference that you change with the temperature, but we have not a real confirmation for all this process. But it's worked really nice. So now the other thing is what happened with the formation of the cathode electrolyte interface, and we make a very we make an experiment to have this this layer, and after we go to the XPS. This is not of course in situ. I say an ex situ experiment, and we show that we had this is for organic solvent, the characterization of the say, and here is for the ionic liquid. So in both cases, like in organic solvent, in ionic liquid also you have the formation of the layer. But in the case of the ionic liquid, it seems that the layer is a little bit thinner. because the ionic liquid is more stable from the electrochemical point of view, at so high potential, like is the case of this kind of spinel. So another thing that is important here is that we don't need to add any kind of additive to have the formation of the say layer. So this is very, very good for all this system. To characterize this in situ way, this say formation is not say with S, but in this case with C. We use impedance spectroscopy, and of course you can model of the with equivalent circuit that is related a different component related al current collector, a say formation, and all the redox reaction with the lithium intercalation. So to do that, we make the impedance at different state of charge. Here, this number represents the amount of lithium intercalates. So we begin with all the system fully intercalate and begin to the process of delithiation, and after delithiation, and we make all the impedance. And here you have the diagram. The only reason that I show you this is here you have the diagram for the organic electrolyte, and you have this is almost two semicircles here. One is the related with the current collector, other with the say formation, and after you have here all the lithium diffusion and related with the intercalation process. When you go to ionic liquid, these processes are really two different time constant, and also you have a greater resistance here. So it seems that even that the say formation is thinner in the case of ionic liquids, you know, it seems that it's more compact because the resistance is greater. That is nice. And after it, you have all again of the redox reaction of lithium intercalation. So this shows that you have the say formation, and the say formation is a different nature that in the case of the organic solvent. So going to the final conclusion, I think that all this can be put in the way that many people is working with ionic liquid in the case of the battery, and also in the case of electrochemical capacitors. And the reason is for the stability of the ionic liquid, and also all the things that you can play with the ionic liquid, trying to find the better one for the system you have. For example, if you go from lithium battery to sodium batteries, the history is a little bit different, because sodium is more difficult to have good salt solubilities in the ionic liquids. But you can play trying to have a solution for all these problems. So the idea here is to show that the ionic liquid could be an interesting electrolyte for batteries. And before to finish, I need to show the people that were at the lab. So this was in last December. Here is without mask, only you can see the face of these people that work, and this way I can give a talk for you. So thank you very much, and I hope that you have many questions for me.
Okay, thank you very much, Professor Torresi. It is very interesting and nice.